In this short video, we're going to talk about how to use the 10-point plot in the DT6 and use it to analyze resonance. So when you start out, you'll be on this screen, and then all you're going to want to do is toggle over to modules and then press the 10-point plot button. And then once you're here, the first thing it'll ask is how long you want each reading to be. 3 seconds is pretty fine for most things, so I'll just go ahead and hit OK for that. But if you want more, you can do that. Then you'll see this input orientation. This just says which way you have your sensors oriented. So if we look here, I have these pointed down. So we're going to go ahead and tell it it's vertical. If you had it normal, that would be like if it was in the horizontal or something. But vertical is most common for my purposes, so I'm just going to leave it there. And then all you're going to want to do is leave the blue sensor somewhere on the machine that you are trying to analyze the resonance of and just leave it there. Don't touch it. And then you just want to take the green sensor here and put it and then move it down the line as you take this arrow and toggle through the different locations. So I'll go ahead and take this first point here with the motor running. And then once the light turns green, you have data there, and then all you have to do is click to the next dot and move the sensor over to the next spot, and then repeat all the way down the line until you get all greens. You don't technically have to do every single one. You can skip them, or you can do them in any order that you want. But we recommend doing all of them because it'll give you the best resolution in the end. So I'm going to go ahead and take all the data, and then I'll come right back here and I'll show you where to go from there. Now that we've gone through and taken all of the data, we can go in and analyze it. So once all of your lights are green, or as many as you decide that you need, you can go ahead and toggle over to the 10-point plot of data and go here. And I'll just mention really quickly, if you wanted to look at an old set of data, you can go ahead and click import here. Once you hit exit, it'll ask if you'd like to save this data, and you can save it and name it whatever, and then you can press the import button to bring it back up. But we're going to go ahead and look at this now. So if we toggle over to the 10-point plot of data, it'll load a bunch of frequencies here, and these are the frequencies in order that the software has determined to be most likely to be resonant based on they have really large amplitudes, and they have amplitudes that significantly change in their value across the length of your measurements. So I'm just going to go ahead and click this first one, and I see, oh, okay, here's the vertical. So here's each of those measurement points, and then I can see the vertical amplitudes, and we can toggle off whether or not I want to see the negative of those amplitudes, because a lot of the time, if it gets close to zero, the real curve would go on top one side and then reverse on the other, but I can go ahead and just toggle that on and off. I can use this cursor here and move across the phase, and I can see the phase versus position here, and I can also see a phase balloon diagram at each of those points. So we can see that right here there's a phase shift of 180 degrees. That's somewhat interesting. I can go ahead and toggle to the other channels if I want and do the same thing with those. And in this case, the thing that is most interesting is what we're looking for is shapes that have kind of the characteristic resonance curve. So one of them looks like just a single half of a sine wave, another one is one cycle of a sine wave, another's two cycles of a sine wave, and so on and so forth. So right now, if we're looking at this, the horizontal one, there might be something here because we can kind of see that there might be some sort of curve right here. The axial are two flat lines, so there's definitely no resonance going on here, at least not at this current frequency. But the vertical is the one that seems the most interesting because this seems to have the two bump resonance curve, the second mode resonance. So we can toggle over to the deflection shape animation, which is the one I personally like, where it'll actually animate the relationship between the amplitudes and phases over time, and you can use this toggle to speed it up or slow it down. And what we're looking for is certain peaks to be really high in amplitude at some locations, but then at other locations we're looking for the vibration to be zero, because one of the necessary characteristics of resonance is to have large amplitudes in some places where the antinodes are, but also some places to have basically 0 amplitude where the nodes are. So here you can clearly see that this point is very close to 0, within the margin that we might accept as noise. And same here, but we have a huge amplitude here, and we're likely going to have a huge amplitude here, but the portion where I was measuring along didn't get all the way over here. And that would help me if we go back to what the original piece looked like. It was on a table on top of another table. So what this is likely telling us is that the table I measured along isn't resonant because the last point was here, but the table it's sitting on is physically longer, and we would probably see this point come back down. So we can have a pretty good confidence of saying the vertical at 42.67 hertz is resonant. So now let's go ahead and look at the horizontal. Well, here we see this point's close to 0, and here it's not, and here it's not. But in this case, you can kind of see it if you really look at it. Other than this point at 3 and this point at 8, which seem to be kind of out of the ordinary, so this might be a case where we decide to take another set of data. But it seems to just be roughly a flat line that's just going back and forth, which is kind of a characteristic misalignment type curve. So this would point to the idea that this phenomenon is actually related to the misalignment of the shaft and not necessarily any resonant. Because, again, what we're looking for is points close to 0, points really far away from 0, and we're also looking for kind of this curved shape going through here, right? Whereas this horizontal one is a much, at its peaks, if we slow it down, becomes a much flatter line if you remove the effect of the 3rd and 8 point. And if we go to the axial, we can clearly see it's not resonant because not any of these points are close to 0. And then from here, we can just toggle to any other frequency and just see if any of the other ones are resonant, because by definition, every object has an infinite number of resonances, and this software is designed to try and analyze all the most important resonances that we might be currently facing in our machine vibration. So here, again, this vertical one doesn't really look like it's resonant because there's only a couple points where it's somewhat close to 0, but this portion here doesn't really look like anything. This horizontal, same thing here. Axial, same thing. So in this case, I might just stop here, and in this case I'm going to, and I would just say that there appears to be a resonant frequency around 42.5 hertz in the vertical direction. And wherever the point between 7 and 8, 0 and 1 seem to be nodes, and if I was to try and mitigate this resonant, I would want to add stiffness or mass to the point somewhere around 4 to 5 because that's where the largest amplitude is, or somewhere over here if we kept measuring.